I hope so far is we have solidified the basic concepts in a simple linear regression model. And I hope to build on that, using Anova. Now, a few things that I'll tell you about Anova. Number one, really, there's nothing new here. It's just a new way of doing some of the stuff that we've already done. I think this is really easy stuff. But before you start thinking, wait a minute, Darbro says we've already done most of this stuff, it's easy stuff, I think I'll just skip on to video number 26. Guys, don't do it. Okay, what we do in this video, this is probably in setting the foundation for the rest of the class. This is an extremely important video. This sets the foundation not only for multiple regression, but for other statistical models that we're going to examine in this class. Guys, at the end of the day, Anova, analysis of variance. Now, don't get this confused with analysis of variance, where we use the technique to determine if the population means across more than two populations are equal. That's not what we're doing here. This is Anova for regression. So instead of examining the ratio of the variance between and variance within, as we do in an Anova, here we're going to be examining other variabilities, other variation, if you will, that are more appropriate topics in regression. So, guys, going to start out by just looking, again, Anova for regression. And what we're going to do here ultimately is examine how we partition out certain very important variations that we call sum of squares. Now, a couple of things we kind of start out with is, we expect through sampling variation. I got my screen wet earlier, and it's kind of sticky, so it's not writing as smoothly as I would hope. So, guys, we expect natural variation in y. And the way that we've examined that variation in y is to simply take a look, that's a yi, by the way, at the differences in the values and the means. And ultimately what we've done is we've created, looked at the sum of the vertical distances squared. Well, guys, that leads me into what we call the total sum of squares for a regression. So, guys, we call this sum of squares total. And the sum of squares total is nothing more than the sum from I equal 1 to n of the variations that we see in y quantity squared. Notice in this situation, x is not considered. The calculation in the total sum of squares simply relies on the difference between the observed y and the mean of the y's. Now, to give you an illustration of this, let's blow up a graph here. Pretend those are straight lines. And if we have our data in here, and I don't want to put the data because I don't want to mess things up. It's easy to think that we have a minimum y and we have a maximum y. And it's also easy to kind of visualize that the mean of the y responses would be somewhere close to the center of the range from the max y to min y. We also, let me just get rid of that because I don't want that to clutter up stuff. We could also see that we have our regression model, which I'll call y hat equals b0 plus b1x. Now, if we come in and examine a point right here, let's call this y1, and I'll tell you what, let's examine a point up here, and we'll call that y2. The sum of squares that I'm looking at right now is simply the length of those vertical distances. So that would be the difference, and then we square that for reasons that we've talked about recently. So again, this distance right here would simply be y1 minus y bar, and this distance right here would simply be y2 minus y bar. We're ultimately going to square these things up, and so the distance, I'm sorry, the order doesn't really matter. Okay. So again, what we got here is we got that the sum of squares for the total is just the sum of our y values minus the mean quantity squared. Now what I want to do is I want to bring in the impact of y. So I'm sorry, I want to bring in the impact of x. So let's bring x into consideration. All right, so when we do that, we can start examining the variability in our regression model. So we're going to examine the variability. Around our regression model. You guys remember a model is just y hat equals b0 plus b1 times x. So back to our drawing, what we now want to do is we want to come in and examine the difference between the y value and what our model predicts it to be. So here we would take y1 minus the predicted value for y1. And guys, it's been discussed many times that we call this the error or the residual. So there should be no surprise that we call this the sum of squares for our error. And guys, we let that be SSE. And this is going to be nothing more than I equal 1 to n, the sum observed minus predicted quantity squared. Now, yeah, I mean, something to think about. I don't know, this is kind of silly to think about it, but I guess maybe it isn't. If we have all of our data, as I've kind of drawn it there, on one line, you might see that in the textbook. You're certainly not going to see that in data that you're actually going to collect, but guys, nevertheless, the sum of square of the error would be 0 in this case. Okay. Now, what I want to do is I want to revisit an old problem. Remember from maybe the last couple of videos, we looked examined ACT and GPA, and I've seen, well, let me see. Actually, I've got it written on a sheet of paper right over here. 32. And we had 2.4, 2.2, 2.8, and 2.9, and 3.5. So guys, what I want to do now is I want to go over to R. And what I'd like to do here is I would like to just calculate the sum of squares total. And I'd like to calculate the sum of squares for the error. Now this is really, really easily done in your TI-84 calculator, but I'm going to use R, and it's, you know, well, it's easily done in R too. So let me close this down. Oh, wait a minute, that's, well, shoot. Okay, well, I shouldn't have closed it down. Well, let's go ACT. Actually, I had this data already put in. 18, 22, 25, 28, and 32. And GPA for this was 2.4, 2.2, 2.8, 2.9, 3.5. Okay, so first thing I want to do, I want to calculate the sum of squares for the total. So guys, what we need to do here is we need to first of all get the differences. Between our GPAs and the mean of the GPAs. And then I just sum up these things squared. And when I get that, I get a sum of squares total of 1.102. Now the next thing I want to do, the sum of squares for the error. Guys, remember the error is just really the sum of the residuals. So probably the easy way to do this is just go ahead and calculate our model. So we want GPA to be predicted from ACT. And then what I can do is I can, let me just show, I've done this before, but what we can do now is we can just get our residuals. So residual squared is obviously going to be the resid for the model, quantity squared, and then I want to do some resid square. Alright guys, what I get there is 0.184, and I'm writing this down over on the chalkboard. Okay, so I want to get back out of this, go get the chalkboard again. Let me see one thing, make sure I'm still recording here. Yeah, I just had a like, oh crap moment. Alright, so guys, you know, again, these things are super easy to calculate. If you happen to put, you know, use your calculator for L1 and L2, sum of squares for the total, what I would do is I would just take, you know, L2 minus the mean, go ahead and calculate the mean, store those in L3, square L3, put it in L4, and then sum L4. If I want to do sum of squared, I just run the residuals, and put them in a list and square each one, store it in something else, another list, and and you know, sum those up. So you know, not a lot going on here. Okay, now something I want you to notice here is that the sum of squares for the total is not equal to the sum of squares for the error. But it turns out that we can make these equal by adding something. And it turns out the same thing that we add there there's the dog again. Blame it on the dog. It's called the sum of squares for regression. Now, if we go back to our picture, which again speaks 1,000 words, we can look at this difference right here, and it would make sense if we're taking two things and we're adding them up and expecting them to be this, that this part right here would play an important role, and it turns out it does because it's the sum of squares for our regression. Examining this point right here and this point right here, we can see that the sum of the squares is just the difference between our predicted value and our mean value. So let's put that into notation. So we're examining the difference between each predicted value and the mean. So guys, the sum of squares for regression is nothing more than the sum from I equal 1 to n of our predicted values minus the mean quantity squared. So guys, from before, so we have that the sum of squares for the total is equal to the sum of squares for regression, which is the sum of squares for the error. And we saw before that the sum of squares was 1.102. .184, is that right? Yeah. So guys, it's easy to see here that the sum of squares for the regression, I'm going to use my calculator because I don't want to make a silly mental arithmetic mistake and find out, you know, here in just a second that that's what I did. So I get 0.918. That doesn't seem right. Yep. So we get 0.918. Now that's a little generic, is to find that by taking the difference between the two. Although that's a way that we will do this often. But you know what I'd like to do here is I'd like to jump back over in R and show the calculations for the sum of squares for the regression. It's probably going to take us 45 seconds to do this, and I think it's going to be worth it to do it. So guys, we'll now calculate the sum of squares for regression. And remember, that's the difference in the residuals. I'm going to do difference sum of squares regression. So what I want to do is I want to take the residuals for the model minus the mean for GPA. I want to square this. And then I want to find the sum of diff SR. Oh, that's lovely. All right, what's going on here? What did we do? Okay, so let's take the residuals for our model minus the mean for GPA. For model minus the mean GPA. Yeah, I want to square those. Wait a minute, I'm losing my mind. This is not what we want to do at all. And I'm sure if we were face to face, you guys would have told me this. We don't want to take the residuals. We want to take the fitted values. We want to take the y-hats, not the residuals. We want to take the fitted model, or I'm sorry, the fitted values. So, my goodness gracious, losing my mind here, guys. Please ignore everything I did up here. Hopefully hopefully you don't get distracted and think that I'm doing something right and come back to the video and think, what the hell is he doing? We need the fitted values, and I think we can get them this way. So let's see if we get the fitted for our model. Yeah, we do. So guys, what I want to do is I want to take, I want to call this the, I don't know, difference for the regression. And I want to take the fitted mod for the model minus the mean for the GPA. And I want to square those. And then I want some diff reg. All right, guys, there we go. Please don't show anybody that. That was embarrassing. Sometimes I get on cruise control here. All right, so I'm writing this down on the other. So, guys, what we got there is we see that the it calculates out to be 0.828, which from the previous is not what we got. Well, the difference must be, don't know, because we're off actually quite a bit, aren't we? We were 0.918. Make sure I didn't do something crazy here. So 1.102. 0.102 minus 0.184. That's 0.918. I am using the right numbers here, right? 1.102 minus 1.184. Interesting. So I have the fitted values minus the mean. I want to square those. I get something way off. So again, the sum of squares for the regression is the predicted value minus the mean. So the predicted value minus the mean, that's the fitted. And if we subtract the mean for the GPA, square each result and sum it up. Well, guys, the only thing I can imagine here is we're getting a rounding error, rounding issue, and that doesn't make sense either. I'll tell you what I want to do. I want to go ahead and run the regression. So we've got our model up here. So what I could do Anova for model, and I'm actually going to, well, get some stuff which I really don't want to show yet. And here I get the sum of squares being 0.828 and the residuals being 0.184, what I'm supposed to get. But the regression, the total sum of squares of 1.102 doesn't add up to that. So 0.82793. What I'm doing, I'm examining this right here, and you can see that the value that I got before of if I can find it, the 0.828 right here is exactly what I should have got, and the 0.184. But when I do the sum of squares, so 0.827, sorry for the confusion, but this has got me buffaloed, as you can tell. Gives me a sum of squares of 1.102. Aha! So it's all about the rounding. Huh. Wow. So guys, well, boys and girls, I am absolutely stumped. So 0.82793 plus 0.18407 gives me 1.012. Damn it. Okay, guys. You all probably, sorry about that. You guys probably noticed what happened. I copied down the sum of squares wrong up here as 1.102 instead of 1.012. So, darn it. All right, that's at least we don't have to throw the baby out the bathwater here and forget everything that. So let's go back and make some corrections here. This is annoying, extremely annoying. So, guys, this should be 1.012, and this should be 1.012. And then when we make our subtraction, I'm going to guess what we get. We get so 1.012 minus 0.184. The good thing about it, you guys are teachers, and I don't think there's ever been a teacher ever that hasn't had something like this happen. So, all right, guys, that's what we need. That's what we actually got from by using R. So, about to lose my mind there. All right, guys, so what we can see is that indeed when you do copy down the correct answers using R, that the sum of squares for the total is equal to the sum of squares for our regression plus our sum of squares for the error, which was clearly illustrated graphically way back when with this illustration right here. So I want to blow that up a little bit. Make sure that you get a visual on this. So if we look at the mean and we look at the prediction, and we have a particular y value, that the distance from here to here is our total. That can be partitioned into two parts. This part would be our regression, and this part would be our error. So remember the difference between our observed value and the predicted value, and then the difference between the predicted value and the mean. Okay, guys, sorry about that, but I was about to lose my mind. All right, guys, let's get into a little bit of why. Well, guys, ultimately what we're doing here is we can see that our data can be explained by looking at the fit of our regression model plus the error in our model. And this also goes by, of course, what we call residual. And we can see, therefore, that the sum of squares for the total is the sum of squares for the regression plus the sum of squares for the error. So we can see that, partitioning this out, the y sub I minus y bar can be expressed as y hat minus y bar plus y sub I minus y hat. And you can just observe that, and you can see that everything works out because the predicted values actually cancel. So guys, this over here is expressed as our deviation of the y, so I would call that just our total deviation. I would call this the deviation of our regression. It's a difference in the predicted values and the mean of the y's. And I would call this obviously the the deviation of the area, or I'm sorry, the deviation of the error, but this would be the deviation. I don't know. Let's just say it's around our line. Now, I think what I want to do here, something kind of cool. Hopefully, I can pull this off. Let's kind of come in and just prove this. Let's just prove that I equal 1 to n of. Hope I can get this all written. Is truly the right-hand side. So what I want to do is I want to kind of put your foiling techniques to test. So let's just let's look at this part right here, and let's expand it, and let's see through some work if we can make that stuff over there happen. So guys, what you can see is that we could, let me see how I want to do this. Okay, if I go sum equal I equal 1 to n, and let me see. It's been a few years since I've done this. All right, let's see. I don't think I want to do that. Let's do the other. Let's do this. Sorry. Let's take this side and see if we can create this. So I can go from that, and I can create that. We're going to have the sum of. I'll tell you what. Let me do this. Let's go some stuff here and make this happen. So I can go y hat sub I minus y bar plus y sub I minus y hat sub I quantity squared. Okay, haven't violated anything there. Now what I want to do is I want to square this. Now, if we think of this as just squaring x plus y, I wish we could just go x squared plus y squared like all of my beginning algebra students tell me that we can do. But what we need is we need this minus y bar squared. And we'll just go ahead and square the last term while we're at it. And then obviously we're going to get 2 times the product and guys, that's going to be quantity squared. That got really messy in the end. Let me try to clean that up. I was trying to write smaller. In fact, that got really messy too. So this is going to be just our y hat sub I minus y bar and y sub I minus the predicted value of I, right? Okay, good. Now, obviously, we can, just like we kind of, what we did from this step to here is we just used a property of summations that the sum of the parts is equal kind of the sum of the total. What we're going to do here is we're going to take the sum of the total inside and break it down into the sum of the parts. So what I would do first of all is I would look at the sum in of y i's minus y bar squared, right? And then I'm going to look at the sum of my y sub i's minus y hats squared. And then obviously I can pull the 2 out, and then it's just the sum of, okay. Now I messed up here. I got, obviously, I don't need a square there because I just squared everything in the step before. I was going to say, where in the hell did that square come from? So guys, notice we don't need this square that I put there because, you know, that's what we did up here. Okay, now, so what we need is well, guys, this value right here is just going to be 0 because of a couple of important properties. All right, let me do a little bit of stuff here for you. All right, this is actually going to be pretty cool. Now let's go back and look at the overall the proof here. I'm trying to get a broader idea of what I'm trying to do here. Look at this right here. If we can actually show that this is the left-hand side. So we took so ultimately when we started out, I just created these where that cancels out. So I have my y sub I minus y bar. So, you know, putting this part together is exactly what we have there. Okay, and again, this is all in an attempt to I guess you got things wrong, to to create this side right here. So the sum of squares for the regression, you know, this part is right there, and this part is the sum of squares for the error, obviously. So I need to show that this part right here turns out to be 0. That 2 times the sum of y hats minus y bar times y sub I minus y hat sub I has to be 0. So what I can do here is I could take 2 times the sum, let's take this term, times that, and then we can take 2 times, what would actually be negative 2, times y bar. That's a constant, so I can pull it out. Minus y hat sub I. Now let me step back and make sure that everything's going good here. We got our 2 times sum, so we can take the y hat out, multiply it by this, take our 2y bar, so it makes that minus because of this minus right here, and then times that. Okay, cool. Now it turns out that this value right here has to be 0 because there's something that we can show that the predicted values times the error, that sum has to be equal to 0. And that's exactly what we got. We've got our predicted values, and this is precisely the definition of the errors. We've also got to show that this is 0, and that's not going to be as easy. Yeah, it is. Yeah, it is. Yeah, it is. Because we know that the sum of the errors has to be equal to 0. So this part right here is irrelevant because the product has to be the observed minus the predicted is just the error, so that has to be equal to 0. So actually it turned out to be actually pretty cool. I'm glad I did that. So ultimately, guys, what we've shown is by creatively, examining this part and rewriting, so creatively starting out, examining this part and getting it into something equivalent to this part. And that's exactly what I did. And it wasn't anything clever at all. I didn't come up with it originally. It's I'm sure something somebody showed me. And then we foil things out, and then obviously this is to show this is 0, and this works out really, really nicely. All right. So here's two properties that are kind of cool. You might want to put those on the back burner. I think I've shown you both of those in a video previously. Probably would have been the very beginning, the first video we did in just the basics of regression. So, all right, cool deal. All right, guys, want to change our focus to degrees of freedom. And it turns out that some pretty cool things happen with degrees of freedom. First cool thing that happens with degrees of freedom is degrees of freedom are additive. And guys, we're going to find out not everything is additive. And we're going to see that here in about in just a few minutes. So what I mean by that is we could look at the degrees of freedom for our total, and that's going to have to sum up to the degrees of freedom for our regression plus the degrees of freedom for our error. So I want to examine each one of these separately. All right. So first of all, let's jump into our degrees of freedom for the total. And it turns out that degrees of freedom for the total, we have 1 degree of freedom. Now, the reason, if you think about the way we did these calculations, we took the y value, subtracted the mean, and squared it, right? And of course, we summed it up. Well, you got to think about this y bar was an estimate of the mean responses for y. So since we've used something in our calculation that was estimate, we have to account for that right here. So we have to subtract 1 for the fact that the y bar was used in the calculation of the sum of squares for the total. Okay, so next thing we'll examine will be the degrees of freedom for the error. And guys, it turns out here that the degrees of freedom for the error is n minus 2. Now, in the error term, we used as estimates of beta 0 and beta 1, which is our regression model, we had 2 things that were estimated, namely B0 and B1. Well, in the calculation of the error, which is our observed value minus the predicted value, and obviously we square that and sum it up, then this value right here, the predicted, was calculated using 2 things that were estimated. So guys, we have to account for that degrees of freedom. Chris, I think you If I remember correctly, you asked a question about degrees of freedom, and I could tell that from your response that we didn't connect. I mean, at the end of the day, degrees of freedom are just the the um, the values that we used in calculating what we're calculating the degrees of freedom for. How many, how much stuff was estimated to make that calculation? So, again, here we had two things that we estimated, so we have to control for 2 degrees of freedom. Now, you're going to see that, again, because the degrees of freedom for the total, and again, these things are additive for the regression, and the degrees of freedom for the error, you're going to see, since this is n minus 1, and this is n minus 2, well, you don't have to have a PhD in mathematics to figure out that the degrees of freedom for the regression is equal to 1. And ultimately, we're going to see that we're going to expand this once we get more predictors. Right now, we're just looking at simple linear regression where we have one predictor. We're actually going to see that the degrees of freedom for the regression have to do with the number of predictors that we have in our model. So, guys, we're making strides now. So let's get on to some other stuff. Now, one thing, I tell you what, before we get on, ultimately what I want to do, I want to get down to what we call mean square terms, but there's an alternate form for the sum of squares of regression. Which, guys, remember that was just sum of squares. Sometimes when I'm teaching, I'll use subscripts there just to indicate what the heck I'm talking about. And this is just taking our estimate of the slope squared times the sum of an expression that you guys have seen quite a bit before. So, guys, put this on your back burner. There's I really kind of forgot about this, but I was kind of thinking ahead in my mind. I ultimately want to get into mean square error, mean square regression, mean square total, and we'll get into what's called an Anova table. And some Anova tables account for more. They take the sum of squares of the total and they partition the variance into a couple of things. I'm not sure what we're going to run into, but you know what? That'd be a great homework problem. Oh, that would be a great homework problem to show that the sum of squares for the regression that we had before is equal to this. So, guys, you may have just kind of stumbled onto something that might be kind of cool. All right, boys and girls, let's move this show on. So, what I want to look at now is something called the mean squares. And obviously, I want to look at the mean squares for the total, which will be MSTO. I want to look at the mean squares for the regression, which is MSR. And I want to look at the mean square for, for the error term. Well, it turns out that the mean square for the total is nothing more than the sum of squares for the total divided by the degrees of freedom for the total. which is the sum of squares for the total over n minus 1. The mean square for the regression is the sum of squares for the regression divided by the degrees of freedom for the regression, which is the sum of squares for the regression over 1, which is just simply the sum of squares for the regression. So guys, if you ever get a test question where you calculate the sum of squares for the mean square for the regression, it won't be a tough calculation. It's just the sum of squares for the regression. And guys, finally, we want to look at the mean square for the error. So that's nothing more than the sum of square for the error divided by the degrees of freedom for the error, which is the sum of squares for the error over n minus 2. Now, just an important comment here. Mean square terms are not additive. Degrees of freedom are additive, sum of squares are additive, but the mean square terms are not additive. So what I mean by that is the mean square for the total will not be equal to the mean squares for the regression plus the mean squares for the error. Guys, let's go back and let's create an Anova table, which I think I already did. Yeah. And so our analysis of variance table. So what I would want you to do here, just kind of cutting through all the stuff here. Remember, we have ACT given and we have GPA given, and so let's just kind of pretend that all the stuff up here we did by hand that we don't have. So what would I want you to be able to do in terms of getting an Anova table? I would want you first of all to create the model. So I am not very creative, so I just call that model, and obviously you put our y's first, our y first. We're not into any sort of multiple Anova or anything here. So we create a model, and one of the first things we can do, very, very easy, we've seen before, is we can look at our summary of our model. We could look at ALV of our model and get just a simple sum of squares. We could look at our model and just get the coefficients of our model. But the big thing that we can do is we can look at the ALV of our model, as I did before, and we get some stuff, right? We get the sum of squares, we get the degrees of freedom for ACT and residuals. And guys, this ACT, remember, is nothing more than the residual, than the regression. It's the regression of ACT on GPA on ACT. But we want a complete table here that gives us our mean square terms and ultimately an F statistic. And the way we do that is by doing Anova linear model. So we're distinguishing in R the difference between an Anova, which examines the means over K groups. So we're looking at the Anova for linear model, and you can see in this situation that we get our terms. Now this is, I really don't like the way this is presented, because typically what happens in an Anova table, and let me go back and get a typical Anova table looks more like this. is you'll have your terms. And of course, first of all, you're going to have your regression line. And then you're going to have your error line. Error. And then you're going to have your total line. And this is the way that I've seen the outputs on SAS and SPSS. So R, to be honest with you, I don't like the way R does it. But hey, it's free. So what it'll usually do is it'll start out with the sum of square terms. So we'll have a sum of square here, a sum of square here, and a sum of square here. And I wish I had the values written down, but you guys can figure it out, okay? Now, next thing we would do is we would have our degrees of freedom, and we would have our degrees of freedom here. And you know what you can notice is since the sum of squares are additive, that these two things added together will get this value here. Degrees of freedom are additive, so when these two things are added together, we will get this value right here. The next thing we get into is we get into the mean square. And the mean square will just take the sum of squares for the regression divided by the degrees of freedom for the regression. So we can take this value divided by the degrees of freedom and get our sum of squares. We can take this value right here, the sum of squares for the error divided by its degrees of freedom, and we'll get our mean square for that term. Now what you'll find out is when you take this value and add this value, add those two together, this is not equal to what you get there. It's also going to be, well, I'm sorry. And that's not going to be equal to what we get when we take this term right here and add this term right here. It's not going to be equal to this. Now the next thing you typically see in an in a table for an Anova table for regression is your F statistic. Now I'm not going to get into that this video, but I'm going to get into it the next video. Wow, that was loud. And our F statistic is nothing more than the mean square for the regression divided by the mean square for the error. And this will follow 2 degrees of freedom. And in our case, it'll be for the regression, which is 1, and for the residuals, it's 2. You guys will get into that more in the next video. So, guys, this is a super duper duper important video, I think. Again, this is the end of video 25. We didn't do anything crazy hard here, but this sets the foundation for things that we're going to do in the future. So guys, talk to you later.